started. Trying to fix the issue with hack 8 right now. Hopefully we'll get that fixed by the end of the day. The issue is something with the server and goes beyond something that I can just do immediately. So today we're going to start on the next module, which is strings and string processing. Fortunately, at least in C, everything that we've talked about over the last 2 weeks using arrays is applicable to strings, because strings are nothing more than character arrays. So if you've got an integer array, it's a collection of integers. If you've got a string, hello world, right? All that is a sequence of characters, HELLO, right? Each one of those is stored in a different spot in the array. In general, strings are ordered sequences of characters. It might be ASCII or it might be Unicode. Over here in C, we have pure ASCII, right? Remember the ASCII text table? ASCII table.com or whatever it is, right? It goes back all the way to the 40s or something, late 40s or early 50s, where this was set up, right? So C really only supports these basic QWERTY keyboard characters. Of course, that wasn't enough. We now have modern, CJK fonts, Chinese, Japanese, Korean fonts. We have Cyrillic. We have even ancient Egyptian, right? And so Unicode was formed in order to extend that into the millions and millions of characters instead of just 120 or 256. 128, 256. Different languages represent strings differently, and so this will be another instance in which C and Java depart quite dramatically. Both of them have rich libraries for doing stuff, but in C, it's going to be a lot more work to do basics, right? Most languages, again, provide a rich library for you to do some stuff, but not necessarily everything that you would want to do. So let's take out the hard part first and talk about strings in C. In C, strings are simply arrays of characters, right? So char, right? ASCII only. You can get Unicode support in C using an extended library or a different character set, because usually a char is only 1 byte, 8 bits, right? That's all you need to represent 256 characters. So if you want support for Unicode, Unicode is up to 4 bytes, right? Because it needs millions and millions of characters. And if you need to support something like that, you're bringing in a library or you're bringing in some sort of an extension, okay? Of course, because we know all about arrays already, you can have static strings, char s with the square brackets, or better yet, most of the times you'll be dealing with dynamic strings, where you have to call malloc to allocate enough space to hold your string, in other words, char star s. And we've seen this before on every single main that we've ever written, right? We've seen char star star s, which is going to be a 2-dimensional array of characters. In other words, an array of strings. Each row is a string. Right? But, and this is a huge caveat here, but, right? For a string to be valid in C, it must, I'm going to put 1, 2, 3, must, 1, 2, 3, there we go. It must end be terminated with a null terminating character. The null terminating character is /0. That is not an O, it is not a 0, it is not null, the pointer null, it is not void, it is not any of the other things that we've come to know as nothing in C. It is something else entirely. It is the null byte. Take a look at that ASCII text table and tell me what you see as the first character there. Decimal value 0, hexadecimal value 0. The character is null. That's the null byte. That's the null character, right? If a string does not end with a null byte, it is not a valid string in C. It leads to undefined behavior. It leads to segmentation faults. It leads to a lot of bad things, right? But again, do not confuse it with 0. It is not 0, right? That is the value 0, right? It is not the character 0, right? That's something different. Actually, single quotes here, sorry. Single quotes for single character. Look over here on the ASCII text table and look at value number 48. What do you see? That's the character 0. Right? That is not the same thing as the null character up here at the beginning of the ASCII text table. It is not null. It is not null, right? Because it's not even a pointer. It is not a pointer, right? It is not void, etc., 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 right? It is something else completely different from all those things. Another common error that I see is it is not the end line character. Right? The end line character that we've come to know and love for going to the next line is what? Slash, how do I go to the next line? N, right? That doesn't look like 0 to me, right? Those are not the same things, right? If an array of characters, chars, is not null terminated, it is not a valid string. And any operation on it is undefined behavior. Anything can go wrong. Segmentation fault. You might just screw up your own memory, right? It might just give you bad results. It could end up being no error, not manifesting itself visually at all as an error. But you will have undefined behavior. So let's jump right into it here. And let's go ahead and create a static array of characters, i.e. a string. Right? So char message, here we go. And I can immediately set it equal to hello world. Oops, let's go with lowercase hello world. There we go. Okay. Now that, come on, over here. There. That creates a new string of a certain length. How many characters are in this string? I see 5. The space is a character, 6, 7, 8, 9, 10, 11, 12. There are 12 characters in here, but what is the size of the array implicitly? What is at the end of that array right now that I don't see? Because the compiler took care of it for me. The null terminating character, right? If you declare it right like this, it will take care of the null terminating character for you, right? Some operations, it will not take care of the null terminating character for you. Others it will. This is one of those. So the actual character array here is going to be of size, what did I say, 12? 12 actual characters here. It'll actually be 13, right? It'll be of size 13. Right? Why? Because it needs room for that null terminating character at the end. Okay? So, again, it will take care of the null terminating character for you in that instance, but the actual size of the array is going to be 13. There's one additional to account for the null terminating character. You can declare strings in another way here. For example, let's go ahead and declare a string here to hold my name. I'm just going to make it really, really big. At most, 100 characters can be in this string, right? And you can even set it initially to my first name here. Right? Now, could I hold a string in this array that is 100 characters? I just had a really insanely long name. Could I? Nope. Why? In order to fit it, I would need how many characters? Always +1 for that null terminating character. So the maximum size of the string that I could store in this particular array right here is going to be 99. Right? So what about all the other bytes in that array right now? Right? CHRIS, that's only 5. Then a null terminating character, it takes care of it for you here as well. What about the other 94 bytes? It's just allocated room. Who cares? Right? It might put in null bytes there. It may or might not. Right? I don't know. Let's try it out. Let me go ahead and grab this example right here. And let's go ahead and print them out byte for byte. Right? There's my name. For int I equals 0, I is less than 100, I plus plus. Printf. Percent. Now, I'm going to print out each character to a line. %C is printing a single character. But I'm also going to print out the ASCII text value of this to show you that there's an equivalence between a character and a number, right? So, end the line here, right? I'm going to print out name sub I, that's the character, and then I'm going to typecast it as an integer, name sub I, to see the ASCII text value of it, right? So for example, lowercase c, where is it? Lowercase c over here in this last column, that's going to be 99. So it's going to print out lowercase c, 99. It'll output lowercase h and 104, right? Dot, dot, dot. Let's see what's stored in the rest of that array. GCC demo. A.out. There we go. Jump up to the top there, 99, 104, right, just like I predicted, and the rest of it, right? 114, 105, 115, dot, dot, dot. The rest of them are all null bytes. Why is it not printing anything? So in the ASCII text table here, these first, I think maybe 32, is it, or what is it? Device control, yep, the first 32 of them are all non-printable characters. These are characters that have different meaning that don't actually get printed out to the screen. For example, null, it's nothing, so nothing gets printed. Right? You can make your, I'm not sure what it would do over here, but we can try to make it sing. What is it? Where's the bell? There, bell, 7. Why the hell is there a bell in our ASCII text table? Well, remember back to the 1940s. What were they typing on? Typing on typewriters, right? What happens when you get to the end? Ding, right? So we have a bell there, right? Bell of 7, right? So what I could do is I could change my S here. Let's see. I could 0, 1, 2, 3, 4. This is just going to be a fun experiment here. I'll change S here to be value alt char 7. There's the bell. Right, now I have zero hope that this will actually sing out to us with a bell. Yeah. There it was. Oh, no, oh, okay, I didn't actually print it. Let me go ahead and move this up here so that it'll actually do something now. I don't have my sound on or anything like that, but yep, looks like it's unprintable. And so if it had the ability to, you know, ding at me, it would have, right? I think it can make it if we want to try really hard. Here, I'll open up a terminal here. Emacs foo.c, vi foo.c. Okay, wait. More bar.c. All right, vi bar.c. All I'm doing here is cut and pasting that. Oops. There we go. GCC bar.c, and I'm going to turn on my sound here, and let's see if we can get it to sing. Get my Mac to sing. There we go. Did you hear it? It was the Mac donk instead of the bell, but there we go. Right? And so I could have changed them all to donks, and then it would donk, 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 donk. Right? There we go. So why? Well, because when was this thing created? In the 1940s, 50s, when they were typing on a literal typewriter, right? And what did it do when it got to the end? Ding, right? So they thought that they needed that, right? And we're still living with that choice today. So you can create, do this, and you can create, strings that are larger than you need, right? This basically wastes space, right? Those other 94 bytes, they're not doing anything, right? But it's okay in some instances if you need, say, temporary buffer space. If you don't know how big the string is going to be, you just make it big enough statically, and then if it exceeds that, then you have a problem. But you just go ahead and use it as a workspace. In C, all strings are mutable, meaning that you can change them. Mutation, right? Mutation is a change in biology. In coding, if something is mutable, it means it's changeable. So for example, I did that right here, right? I changed my S to a donk, right? To a bell. I could go ahead and change this so that, say, name sub 0, right? The first value here is no longer a lowercase c. I'm going to correct that and make that into an uppercase C here. Right? Let's go ahead and get rid of this printing and just print out the entire string. Printf. Name is equal to %s for a placeholder for strings, right? And name. And we'll see that it has been changed, right? It's been changed to Chris, uppercase CHRS. Now remember, I made it large. It's able to hold up to 100 characters there.
So let's go ahead and put in my full legal name. Names of, so CHRIS, that's 0, 1, 2, 3, 4. 5 would be O, right? Name of 6 would be P. I'm changing it to Christopher, right? So name, there's got to be a better way, right? I have to type all this stuff, right? Is equal to H. Okay, that's good enough. Let's go ahead and see if it works. Yeah, it works. Okay, so I've got some more work to do here. There must be a better way, right? I'd really like to do something like this. Reset it to be Christopher. Now you can do this all day long in Java. This is not how C works, right? Let's even try to compile this. Right? Assignment of expression with an array type. You can't do that after the, you can do that when you declare something because that's the compiler taking care of it for you. But after you've declared it and you try to change it down here, that's a compiler error. You can't do that, right? Instead, what you need to do is you need to bring in a library to do it, and that's the string library. Right? You need to copy one string into another string, and you need to make damn sure that you've got enough room to do so, right? Because memory management is on you, the user. Okay? So here's a preview of how to do that. This will not work, so I'll comment that out. Instead, this will. Right? I want to str cpy. Str is short for string. Cpy, what do you think that's short for? Copy, right? And I want to copy into name the string Christopher. There we go. Topher. That's how you would do it. So note the order there. The thing on the right-hand side is getting copied into the string on the left-hand side, right? It matches your attempt to do something like this, where you take the thing on the right-hand side, use the assignment operator to put it in the thing on the left-hand side, okay? That will require, of course, the string library, string.h. There we go. And that works. Okay, I'll put this over here in the notes. There we go. All right. So what we just witnessed was string assignments, right? You can't use the equals operator. After the initial declaration, you can manipulate individual characters all you want. You can make them from caps to lowercase. You can change them to bells instead, right? But you cannot reassign the entire contents of the array without the usual assignment operator, right? It will not work, right? Instead, you must use the string libraries Str Cpy Function, right? And again, the string library is in, oddly enough, string.h, right? And the Str Cpy has a function signature looking like this. Dest is short for destination. SRC is short for source. And so what it does is it copies the contents of SRC into the string dest, right? In other words, right to left, just like the assignment operator, right? They wanted to keep that pattern of taking things on the right-hand side and moving them into the things on the left-hand side. Tell me about the source. We've got char star, right? That's a string. But what else do we have in front of source right there? What keyword? Const. What does that tell you about that? The const in front of the source string indicates no changes will be made to source. But in contrast, is there a const in front of the destination? Why? What if there were? Could you copy anything into it? Nope. So the lack of a const in the dest means it will be changed. And that's what we want, right? That's the whole purpose of using this function. It is your responsibility. responsibility to ensure that the source string is a valid string, and it is your responsibility, I don't want to type that, to ensure that the destination string is big enough to hold the source plus the null terminating character, which it will take care of for you. Right? It'll copy over the null terminating character for you. What I mean by that is, let's come over here and try to, well, okay, I don't need 5. I don't need 100 characters to hold my first name, CHRIS. Could I do something like that, first of all? Is that enough? CHRIS. What am I missing? The null terminating character. In fact, hopefully the compiler will catch this. Oh, there we go. Yep. Writing 12 bytes into a region of size 5. Okay, well, wow, really good. Okay. This is the note that I was hoping to see. Let's get rid of this stuff for a second. All right, there we go. All right, so are you going to complain about that? Hopefully, yes, thank you. Well, it's an unused name. Never mind. It's the wrong warning. Right? It should be saying, well, wait, this is of size 5. I can put CHRIS in there, but I can't put the null terminating character in there for you. That's not big enough. Right? If I want to make this exactly big enough, what would I need to make it? 5 plus 1. Right? Now that's going to work. Right? Let's go ahead and try to string copy into that. And brilliant. Wow, it's able to detect this. Warning, you're copying 12 bytes into a region of size 6, and that overflows the destination string. Note, however, that it's just a warning, right? And it probably goes away if I take away the wall flag. Oh, no, it doesn't. Wow, okay. That's a severe enough warning that it's going to be there by default, right? Awesome. Very good compiler, right? Not all compilers are like that. I'm pleasantly surprised that GCC now has that. Right? All right, well, it's just a warning, right? Let's not heed that warning. Let's go ahead and try to do it anyway. There we go. That's what I've been waiting for all semester. Stack smashing detected. Right, what have I done? Where is this string located? Because it's a static array, it's located on the stack. There is this stack frame for main, right? And all of its variables are in it. If I had variables int x, y, z, right? Those variables exist in the stack frame, as does my name, right? There are 6 bytes here reserved for my name, right? And I'm trying to write 12 bytes, right? My name here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why did it say 12 bytes again if there are only 11 characters? That null terminating character, right? Never forget that, right? So it's trying to write 12 bytes into a place that is only 6 bytes, right? And where is it located? In the stack frame. I've smashed my own stack, right? I've overwritten memory that belongs to my program, right? But it kind of screws up the entire call stack. And that's why I'm smashing my own stack here, right? And it terminates it with not a segmentation fault, but a stack smashing event. Very cool. Right? I could instead, go Chris, right? And change it so that it's exactly as much, unused variables there, but whatever. But that'll work, right? No stack smashing event there. I could make it shorter, right? C, like just my initial here with a period, right? And that'll work too, right? But you can never go longer than what you've already created. Right? If you need to go longer, what you need to do is you need to start making dynamic arrays, right? So, before we get there though, let's talk about some other operations, right? Or other basic operations. Right? You can determine how long a string is, the number of characters in it, using strlen. Right? So what do you think len is short for? Did I put it in there? Okay, how long it is, long is length, right? String length, yeah.
Why can you
good question, right? So of a regular array, if it's just numbers, 5, 10, 20, 30, 40, where do I stop? I don't know. But if it's a string, a valid string, oh, C, H, R, I, S, null terminating character, I know where to stop. That's why C does it this way, right? Because you can have, it was always intended that these things be used as byte buffers, pure data buffers. And you need to know when, like if you've got a long buffer and you're only using part of it, you need to know where where the end of the buffer is, right? So strlen, all it does is it does something like this, right? So let's write it. Int counter, started out at 0. For int I, or let's go while, because I don't know how long it is, how long this string is. But while, say, name sub I is not equal to the null byte, the null terminating character, then I'll say counter plus plus. Right? And of course I need I here. Actually, I'll just use counter. Right? And printf, it has %d characters. Actually, let's just go ahead and print it out. %s has blank characters and name. There we go. And then we can play around with this, right? Let's go ahead and get rid of this, and let's go ahead and go up this to Christopher, right? And I won't tell it how big it is, right? The compiler will take care of that for me. Yeah. Unused. Let's get rid of those. What's wrong? Oh, name and counter. There we go. GCC, a.out. There, Christopher has 11 characters. If I change this to Michael Burke, there's my full name, right? There we go, it's done 26 characters. All it's doing is going through and counting them up until it gets to that end line, that null terminating character. Now, I can do the same thing with strlen, right? Counter is equal to strlen of my name, and strlen says that whatever my name is has those characters, that many characters. So these should agree, right? There we go. And it agrees that there are 26 characters in my full name. Let's take out my middle name here. Experiment again, GCC, right? And 18 characters, 18 characters. Now that is including the space there. What it does not include is what? Let's take this down to just CHRIS. 5 characters, right? So what does that tell you about the null terminating character and whether or not strlen counts it? Does it count it? Nope. So know that, right? Again, it only works on a valid strings, right? It does not include the null terminating character, right? And again, all it does is, I'm sure that it has a better while loop than I just wrote, or some bit trick or something like that, byte trick, that it does, it's more efficient. But it runs through. It literally runs through and counts up the number of characters in it until it gets to the null byte. Right? That's why if we try to do something like this, Str Cpy name something that is too large, stack smashing event here probably, hopefully, yeah. Yep, okay. But strlen says that it was still able to get it, right? But eventually I smashed my own stack, right? So I was able to do it, right? I was able to count up those characters, but by that point I had already corrupted my memory and it dumped my program. It aborted my program. Right? Okay. So it does not include the null terminating character. Another one is concatenation. So string concatenation in C means string concatenation simply means appending one string to the end of another string. Right? So in other words, if I go Chris plus, or let's go like this, Chris
plus Burke. Something like that, right? Now you're familiar with that from Java, right? All you have to do is plus, 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 plus. Not all languages support that, right? For example, does anybody know any PHP or Perl? PHP and Perl don't use the plus operator there. They use the period. That's the string concatenation in PHP and Python. What about, or PHP and Perl, excuse me. What about Python? Python uses what? I thought there were some Pythoners in here. Yes, no? All right, Python uses plus, except that if you ever try to concatenate things that are not strings, like this, can you do that in Python? Nope. What happens is it donks out saying that the 12 is not a string. What you have to do is you have to surround it with a string, turning it into a string, the characters 1, 2, instead of the number 12. Right? Some other languages, like C, for example, there is no concatenation operator. Right? It's not a first order operator. So to do this in C, you use a function. That function is Str Cpy. Do we start to, or Cpy, cat. There we go, sorry. All right, so do we start to see a pattern here? String functions in the string library start with str, short for string. And then there are usually 3 or 4 other letters or something like that, which is an abbreviation of what they do, right? Cat is short for concatenation. Here's what it looks like. In fact, it looks exactly like Str Cpy. You take the source and you append it to the destination. Right? It appends the source string to the end of the destination string. Right? Again, it assumes that both, in this case, both are valid strings. Right? It will take care of the null terminating character for you. And it assumes that the destination is big enough to hold both strings. Right? If it's not, you have undefined behavior, right? Okay. So let's take a look at this over here. There's my name. I'm gonna pump it up here again to 100 just to make it big enough to hold whatever I want, right? No, I don't want Chris. I want Christopher. After I've done that and it's a valid string, I could go ahead and str cat, name, space, or let's go Michael first. See what that looks like. And then concatenate my last name, Burke. There we go. And let's just print it out. I'm not interested in how long it is. Name is equal to %s. Okay. And this is definitely big enough to hold Christopher Michael Burke. But what have I done there? Is that well formatted? No. So you can go ahead and put in spaces, right? Space, space, wherever you want. Right? There we go. And it's a well formatted string. It's null terminated. It takes care of everything for you. Right? If that's not big enough to hold your name, 1,000 will be. Right? If that's not big enough to hold you, like every single person at UNL's name, can I go ahead and make it that big? I don't know, how big is that? 100 million bytes. That's 100 megs, just short of, right? Okay, what's gonna happen here? Segmentation fault instead of a stack smashing event. Can I make big static arrays like that? Nope, I have a stack that's limited to 8 megabytes, not 100 megabytes. And so what happens is it gets full and stack overflow. Right? So you do have to be judicious if you're going to use static arrays for strings. You should probably almost never use static arrays for like numbers or something like that unless you are absolute assurance that you're only going to have like, you know, a dozen or 100 or something like that integers. Right? All right. What else can we do with this? With only 15 minutes left. let's talk about two byte limited versions of these things. So byte limited versions, right? Oh, actually, before we do that, let me ask a question here. Let's go ahead and, you know what? I don't want it I don't want it to print out like this. Let's go ahead and go back. There we go, right? What I want it to print out my proper title, right? My doctor, there we go, right? And if I did it like this, I'm hard coding that title right there, right? Then it prints out Dr. Christopher Michael James Burke, or my other name. I have two middle names, but anyway. No, I don't want that. I want the title as part of that string. I want to put it in there, right? Can I prepend it? Now in Java, you could do something like that, right? Name is equal to doctor plus name, right? You could do that perfectly fine in Java, and then it'll prepend it instead of concatenating it, right? Prepend, append, right? We don't have, is there an antonym to concatenate? Anybody? Forwardnate? I don't know. But you can't do this in C. Right? What would I have to do? I would have to shift everything down by 3 bytes in order to make it room for that I guess 4 bytes for dr period and then a space, right? So some things are more convenient than others, right? There is no str prepend, right? Something like this. Right? There's nothing like that in the string library. You can write it, right? And maybe that's a good exercise that we can do later, right? Okay. But let's talk about the byte limited versions first. Yep, there we go. All right, so both of those functions can have a different cousin function here with a different name, strncpy and strncat. They both take a third argument here. That's the maximum number of bytes or maximum number of characters that you want to copy or concatenate, right? So basically what I'm saying is, let's go ahead and come over here and let me create another string here, char full first name, right, is equal to Christopher. And it needs to be a proper string there. And then I'll have char short first name. Right? And I'll just make it big enough, say 100. Right? What I want to do is I want to copy CHRIS into short first name. Right? I don't want the entire thing. Right? So let's go ahead and go with short first name. There we go. So what I can do, if I just use Str Cpy into short first name, full first name, right? It's going to be big enough to hold it, but it's going to end up copying my entire first name, CHRISTOPHER, right? What I want is strncpy, and I want you to only copy the first CHRIS 5 bytes, okay? And when I do this, it seems like it's going to work. Right? It looks like it's going to work. Right? I wonder if valgrind will catch the problem that I'm causing here. Valgrind, a.out. Yes, one error. Conditional jump value was created on the stack allocation. When I tried to print it on, I didn't tell me the line numbers here. The G flag there, run it through valgrind, and what line number is it at? 15 and 7. It was created on line 7, right? Or there's main on line 7. And on line 15, when I try to print out short first name, it is invalid. Why is it invalid? strncpy will go through and copy exactly what you tell it to. I only want the first 5 characters. C, H, R, I, S. By itself, CHRIS, is that a valid string? What's missing at the end? The null terminating character, right? So, strncpy will not necessarily take care of that for you. Instead, I want short first name of 5 to be the null terminating character manually here. Right? Why 5? 0, 1, 2, 3, 4, CHRIS. 5 will be the last one. Right? That's why I put the null terminating character. Let's try this again, and let's run it purely. Right? That still works, and valgrind should report 0 errors now, right? Because it was a valid null terminated string. So Valgrind can be used to determine or to detect, in some cases, that you have failed to validly null terminate a string. Right? So, again, it will if either function sees the null terminating character within the first n bytes, it will be copied over, right? And it will end its copying, right? It only copies at most n bytes. It stops either at n bytes or the null terminating character. Right? Otherwise, the null terminating character becomes your responsibility. Right? So it can be used to create substrings. Right? We'll talk about that on Monday. Right? But for now, let's go ahead and just go over to Java here and ask ourselves, do we have those problems? What do I have in demo? Oh, this is the midterm. Review, get rid of all of it, get rid of this. Everything that I did today in C, it's super, super easy in Java. What do? You want a string, you go ahead and make it whatever you want. Chris, there we go. It should be capital S, or capital C, excuse me. Name is equal to, okay, there we go. Nope, it should be my full first name, Christopher. Do I have to allocate memory? Does this even look like it's an array? No, it is. Here's the actual string class in Java. Tell me, how does it store things? As an array of bytes, right? So it is actually a string. Now, it stores everything as an array of bytes here because it supports Unicode natively, right? What I could say is, Christopher, let's go ahead and print these out. Print our system.out.println name, right? Run this and see that it prints my name and I don't know, smile emoji. I've shown this before, but you can go ahead and embed, any Unicode characters whatsoever into strings. Here, I'll just put it at the end. There we go. Oops. All right. I just copied random crap from the internet here. The smiley there is definitely an emoji. I'm not sure what the rest of this stuff is, Cyrillic or something, whatever, but it'll work just fine. Oops, no. Why are you not happy with it? My terminal is not happy with it. Because I didn't save. There we go. So you can put whatever random crap you want into strings in Java, right? And did I have to expand the memory? Did I have to make sure that it was big enough? No memory management in Java. Instead, it's all taken care of inside this class, and I don't have to worry about any of it. The thing is, the real gotcha is that strings are not mutable in Java. Strings are immutable, right? If I do something like this, name is equal to Chris, there are two strings in memory. The one with a lowercase c and a one with a uppercase c. Right? It is not changing the original value here. Right? What it is doing is it is creating a entirely brand new string over here, and then it's throwing away this old string and making name point to this new one over here, right? Or to refer to it. It's not a pointer because there are no pointers, but there's a reference. Initially, it's pointing to the one over here with lowercase c. It throws that away, creates a new string with capital C, and makes the reference refer to that one instead. Right? So strings are immutable, and immutability is actually a very, very good thing, right? Because it means that you've got thread safety automatically. So when you do something like this, you are not changing the string. You are changing what this refers to. You're changing it into this new string over here. Right? So everything that I did, from Chris to a capital C Chris to Christopher to that emoji crap, that was creating a new string every single time I reassigned it. So keep that in mind, because when you go to use the string library, say name dot to lower uppercase, I want all caps CHRAS. Let's go ahead and print it out. System.out.println name. Did that change name? Let me make sure that that it works. First, it'll print out lowercase c-h-r or uppercase c, lowercase h-r-i-s, right? It didn't change it. Why? Because it can't. It is immutable, right? This to uppercase here returns a new string, string foo, right? And the string, the new string, is changed to uppercase c-h-r-i-s. So remember, strings are immutable. Once they're created, you cannot change them. You can put emojis into the YouTube chat too. Right? Everything supports emojis natively now, right? But C is old school that way. I'm sure that you could put this into the IDE because it's a web browser based IDE. But no, smiling face emoji here. I'm sure actually. I think that this would even compile. Ugly. And what will it do if it runs? Oh, I'm not actually printing it. So we'll end it here if this works or not. I will be very, very dismayed to know that this is supported natively, unfortunately. So we're in 2022 now, right? And these things have infested our code. All right, any questions? All right, then we'll pick it up there on Monday. Have a good weekend. We hope to have midterms and hopefully hacks graded this weekend.